Hello everyone, good to see you all here. Today I'm going to talk about the art of introspecting OpenSearch. So we have heard all the good things about the OpenSearch and the variety of use cases, right? Primarily log analytics, search engine, security analytics, vector databases, right? All of these are getting powered by OpenSearch. But now I'm going to talk about the common challenges. So common challenges can be categorized into two parts. One is the performance part, right? You expect your queries to have certain latencies, right? You don't expect the P90 or P100 to exceed your SLAs. The second part is the resiliency, that your cluster, your deployment, it doesn't break down with uncertain things like nodes going down or disks slowing down or let's say any network packet drops, right? All of this. So the cluster should be resilient to all of this, right? So today I'm going to talk about various tools we have at our disposal to find out the issues and solve for them. Let me start with the first problem. So in a production cluster, what we see is a slowdown of request. Now, how do we go about that? So here on the slide, we have two graphs. One is CPU utilization. The other one is request rate. We see that though the average request rate has remained same, the maximum has quite stepped up. Similarly for CPU utilization. So average again is the same, but max again has stepped out. Now, what do we do next? We go to node level metrics. So as highlighted, one of the nodes has much higher search rate as compared to the other one. This points to an imbalance in the cluster, right? Some node might have more shards which are taking in more search rate. There might be skew in the number of documents, or it might be that it is hosting more shards, more hot shards, right? So this is how you get to know the root cause of that. Let me talk more about how we get these graphs, right? So OpenSearch exposes a bunch of stats in the stats API. What we can do here is we can have agents polling the cluster or every node level periodically. We can get this metrics and push to a metric sync. It can be an OpenSearch cluster, AWS CloudWatch, InfluxDB, or any time series database which you'd like to configure. On this, you can set up alarms so that anything goes wrong, you get alarmed immediately, right? And you should set up retention policies as well so that the data doesn't accumulate ever, maybe 7 days or 30 days, whatever you would like to see the performance till that point of time, right? Let me talk about the critical stats, which are our first level of defense. The most critical one would be the resource level ones, namely CPU, JVM, and disk. In the previous problem, we saw that the CPU was becoming a bottleneck, resulting in a search latency spike, right? Similarly, the JVM, what happens if your garbage collection is happening very frequently and still not able to free up the memory, right? That is a problem that will slow down your request by a lot. Disk, if your index state management is not running perfectly, you may see the disk getting full, right? And then the cluster will turn red. Your existing ingestion will also stop. So these are the metrics which we need to very carefully monitor and alarm. The second, we recently added doc level metrics as well, 2xx and 4xx, that tells you that how many documents were ingested successfully and how many were rejected, right? Latency metrics, so we have total search time and indexing time which the cluster spent, and we have total search request and indexing request as well. So we divide by that. We take the previous value, we take the next value, and we find out that what is the average search latency and average indexing latency. The thread pool metrics, it's a kind of resource metric as well. We can see that what is the bottleneck here. Our thread pool is getting exhausted. Do we need to tune it all, right? So what is the use of the stats API? So this is the first level of defense, right? Any problem, you turn to your stats API wherever you are storing it. It is very useful when we want to determine if there is any change in workload or any node level anomalies. Let's say your one node has a slow disk, right? So the indexing rate will drop. The indexing latencies will spike. Maybe the thread pool will also spike, right? It is getting busy, but it is not able to complete the work, the rejections might be higher as compared to other nodes, right? So you can easily identify any node level anomaly, and then you can decide to terminate that node. Shard imbalances, like in the previous example, there was a clear shard imbalance problem, so we can find it out as well. And with this, we can identify the bottlenecks, if any, very quickly, right? So what are the limitations? Like I said, it only provides aggregates. So you would only have average latencies, not the P90 or P100, right? So we can't find out the outliers there. And index level and shard level visibility is too costly, because what if you have 200K shards, right? Your response will be too bloated, and it also puts a lot of pressure on your OpenSearch cluster as well. So it is not advised to do it very frequently. And storing that at such cardinality is also costly at scale. Let's come to a second problem. So we see that the searches are timing out. The request, you can see the request timeout after 60 seconds, right? Now the stats API doesn't help us here, because it only gives us the average latencies, not the, even if it gives the latencies, it will not provide us with the details on how to go about it, right? So we turn to performance analyzer. What performance analyzer gives us is, it gives us numerous performance metrics for a cluster. It gives us OpenSearch metrics as well as node level metrics as well, right? The network metrics or the disk metrics, all of that it provides, and it provides it on index level and shard level basis as well. So let me go back to the previous problem, right? How do you go about solving it? So we just look at the a CLI, the network CLI provides, to see that one node has a very high network in and network out. So it increased the search latency to greater than hundreds of seconds, right? So that's how you can see in live real time that, hey, your query is causing this imbalance on one node, and that's the root cause, right? So I'll go briefly talk about the performance analyzer architecture. So performance analyzer is a plugin which runs inside of OpenSearch. It generates events and put it into a TempFS. We have a reader process which periodically polls for the updates and compacts it into a metric DB file. We also have a bunch of root cause analyzers running over it, which can detect problems in real time as well. The above graph, which I shown in the before, was a perf top one. So it reads out the metrics from the reader process. An important thing to note here is that reader can communicate with other reader processes. So that's how we get the cluster level view, right? That's a distributed part of it. So let me jump to another problem. Now, again, we are seeing slow queries. We see that the node is becoming a problem. Now, how to go in the next level of detail, that what is actually problematic? We also see high CPU. The CPU is, again, on a higher side here. Also, the request rate is also higher. Now we turn to profile API. Now we run our queries with the profiling option, and we find out that the rewrite time is about the magnitude of the search latency. So in the whole profile output, we see that every shard has got high rewrite time, right? Now, how do we go next about it? We use Hot Threads API. Hot Threads is an OpenSearch API which tells you what your cluster is doing, right? So in here, we see that the parent-child join query is taking a lot of CPU, and that is across nodes. And you can see that it is taking 90% of the thread time here, right? So in combination of Hot Threads and Profile API, we have identified that the parent-child queries are the culprit. And it points to that our data model, there is an inefficiency there, which can be solved by denormalizing the data. That was the conclusion we had from the above solution. Now, what does Profile API gives us? It gives us the individual components of a search request through which we can use it to debug the slow request path. What it doesn't give us is the network latencies, the time spent in the queue, the time spent in the search phase. One important thing to note about here is the heavy resource usage. So it's not, if we are using Profile API, the search itself becomes, it takes more time for the query itself. So it's not supposed to be used in production. It's a reactive measure. When you see a problem, you use Profile API and see what you can do with the results. A bit about hot threads, it gives us what is running hot in your cluster, and you can identify the bottlenecks and solve for it. I'll come to the most obvious thing that everybody know of, but few of the knobs here which we can use. The slow indexing and search logs. Here we can specify that this is the thresholds beyond which I want to log my indexing request or search request, right? So you can see what queries are taking very high time, right? The second is the error and debug logs. So we log error logs by default, but you can enable debug log and trace log as well. So you can see what is happening wrong with the cluster. This is important when there are specific errors, right? Let's say there are few exceptions. Indexing and search logs would be helpful in case of latencies when you see high latencies, but the error and debug log are helpful when you see errors in your indexing request or search request, right? You can see what is going wrong. The third option is the HTTP transport tracer log. So here, you can specify your index patterns, and then any request corresponding to that index pattern comes, it will log for that specific request. So these are the all tools I had. Now I'll hand over to my colleague, Gagan, to take you to the next of the course.
So like Gaurav discussed, we have a lot of tools available to debug, but still there are few things lacking, and those are part of the limitations. So we'll see how we are addressing them. So this is very basic ask that this is a request journey of a typical search request in OpenSearch, where the request lands up on a network layer, then it gets converted to REST action. It goes to transport search action because it's a search request, and goes to coordinator node. From there, it gets distributed to the corresponding shard sitting on different nodes. So today, we don't have any mechanism to see how we can attach all these, when the request travels through all these code paths, how we can attach them back against a one request ID or something, so that we can see, okay, what happened to my request, which phase took more time. So we don't have that sort of mechanism today. There are options like slow logs, but that also lacks the information to stitch back all the various log lines. So like we discussed about stats API, it's great to fetch all the metrics. You can scrap it, it's okay. But if you see the red line, so that is a P50 percentile. But what stats API is going to give us is the average. So average sometimes doesn't make sense to find the outliers and all. So we want something to be more granular. Like if you see the blue graph, it gives you all the spikes. This is representing the same data. So in order to fix that, we have come up with a telemetry framework. This is an experimental feature we released in 2.11, and we are working towards making it general available. We want all your contribution here to go and try it out and let us know what are the new features, what are the fixes or new things that we need to add in that. So it primarily consists of two things. One is distributed tracing framework, which the problem one that we discussed, it will let you have the entire trace of a request so that you can understand, okay, this request took how much time in which phase. And if we go, there's a metrics framework, which is going to give us more granular metric data, and all we will talk about it maybe in the coming slide. So distributed tracing, it gives you the visibility of a request when it travels through different code paths, like how it's moving, what are the bottlenecks in the code, or maybe visibility per se. You can just understand, okay, if I'm running an aggregate search query, which all search path it's going through. It also gives you understanding the performance bottleneck. We see like shard skewness is a very common problem. So with that, you can simply identify, okay, if search phase, query phase on shard 1 took more time, then we can go further and debug that. It also helps you troubleshooting if there are errors. Those errors will also be part of the traces span so that you can see, okay, in this request, what failed. Today, you will have to go, let's say, n number of nodes and do the log scraping, or maybe you put your logs back to OpenSearch and do the queries on that. To some extent, it helps with the capacity planning also, where if we know our workload, we know, okay, how my requests are going to perform, what are my execution paths. To some extent, we get to know, okay, how much resources we want. So there are three major components of a tracing, distributed tracing. One is trace, which represents your entire request. So whenever your request lands up on OpenSearch, we create one new trace ID, and wherever this request goes, we carry forward that trace ID. If you, let's say you are having some client which is already running some telemetry functionality, it is already having configured for distributed tracing, then you can pass on that same trace ID also, and the system will start attaching this OpenSearch request to that trace ID also. The span is a logical smaller unit of work within that trace. It could be query phase, it could be, let's say, fetch phase, anything, and all these spans can make a tree and become a trace. Carry forwarding the trace information, trace ID, and a couple of other attributes, we use the context. And for OpenSearch specifically, we are piggybacking on the thread context that OpenSearch offers. So now the same request that we have, same problem that we have seen in the first slide, you can see we are creating the spans around it. For the REST action, we have created a span. So this is the first span, so it's having parent span as a root. Then we are going for transport action. Then all other spans are getting created and they have their parent. So all that get attached and you can have a one request level view. What happened to your request, which all code paths it has gone through. So for implementation, we have created a tracing API in the OpenSearch core. So all our components like search, indexing, transport, thread pool are using that API to emit their instrumentations. And the API's implementation is provided through a plugin. So that is a telemetry plugin you need to install when you want to enable this feature. And it is written based on OpenTelemetry. And we are using the concepts of OpenTelemetry. But those are abstracted in the plugin so that if you want to use anything else as a telemetry solution, so that can easily be plugged through a plugin. So then these created instrumentation or traces go through in-memory buffer, and there is an exporter which exports them to the so there are two options. One is you can have your OpenTelemetry collector running locally, and that will help you exporting these traces out to some external store, or you can directly write from exporter to the external store, but that is not recommended since it may put some pressure on your OpenSearch node. So because of the time constraint, I'm skipping through these slides, but this basically how you can install your OpenSearch. Since this is a feature plugin, you will have to enable these feature flags. These are already there in the blog post. You can simply refer them and start using it. This slide is a little important because we have run a lot of performance tests and came up with these numbers. This is, it tells basically when to export. So what we have configured is if the max queue size reaches 2048 or the time reaches to 2 seconds, whatever happens early, we just export the spans, and the batch, we do export in the batches of 512 spans. So this is the request that we were discussing. So this is the trace of that request. It first lands up in the, if you see, it's a hierarchical, right? So first it lands up on the network layer. From there it goes to REST, and then it goes to transport. And from transport, if you see, there are it goes to query phase, and in the query phase we have, that is a coordinator level of trace. Within that, if you see, we are running 2 query phases in parallel. One query phase internally is calling the fetch phase, that is based on the nature of the query, and other query phase was not having any data, so it did not go through the fetch phase. Just 1 second. Yeah, so here if you see on the right side, you can easily see which phase took how much of the time, and we can easily identify. It's not visible here in the slide, but you will get to know, okay, this span was created on which node and which thread it was running on, and all that stuff you will be having as part of the tags information. So there are a couple of challenges. One is coverage. So adding instrumentation in the entire OpenSearch code base is a challenge. So, but we have added to a lot of generic constructs like network layer, REST layer, to some extent on the transport layer, as well as the searching and indexing paths. We are also doing it for batch operations like merge and all, so that we get to know the full view of the cluster. Another challenge is scalability, where because you cannot trace each and every request. It's going to be very costly, as well as you require a lot of storage and a lot of resources from the OpenSearch node itself. So there is an option called sampling, where you can intelligently sample which all requests you want. We will talk about it. Then there is a performance overhead. We did a lot of tuning, and with that, we are able to achieve very minimal overhead when the tracing is being run through the cluster. So there are two ways of doing the sampling that OpenTelemetry gives. One is head-based sampling. This has to be decided as and when the request lands up in a system. So you need to decide, okay, whether should I trace it or not. So it cannot be backed by some intelligent data or anything, because you don't have any information like any error code, latency, anything. So there, the best thing that works is probability. So you can configure, okay, I want to let's say trace 50% of the traffic. Then the reverse is tail-based sampling. That decision has to be made once the entire request is complete. It goes to your local collector. From local collector, you will have to collate all the spans, then create a trace view and decide, okay, I want to keep it or not. Both head-based sampling, we have implemented few approaches for specifically for OpenSearch, but tail-based sampling is little hard for OpenSearch scenarios if you are running at a good scale. Then we have created an RFC. We came up with a custom sampling where we are trying to mimic the tail-based behavior within the OpenSearch node itself, so that we can take that call without even pushing to the local collector. So there is a debate going on, so you can go and read about it. So head sampling, though, there are a couple of options. On demand, like you can simply, if you want to, you are debugging, there is some request, you know, okay, this request is creating an issue, you are debugging, you can put trace equal to true in the header, it will bypass all the sampling thing and it will get sampled. Then probability is there, transport action probability is there, and you can chain all these samplers you can chain them, so that if one sampler is not able to sample, then it will move on to other sampler and so on. So now moving to metrics framework. Metrics framework, as we all know, comes with observability, troubleshooting experiences. It also provides you the granular view. And if we are going to compare it with stats API, then it's very simple to implement. Creating a new stat is always a challenge. You need to identify, okay, which API it should belong to, whether it's an indexing stat or something else. So, but here it's like a simple log line. You can put it as a metric. So metric architecture is also same, but here if you see, instead of tracing API, we are writing to a metric API, and implementation is provided by telemetry hotel plugin. We can have separate implementation for metric also. Instead of exporter, now we have a periodic exporter. It by default aggregate them for 60 seconds and then publish it to the external collector. So there are 4 types of metrics being supported today, which are counter. Those are monotonically increasing metric counters. And if you are having some metric which needs increment as well as decrement, you can use up-down counter. Histograms are here, which helps us with a more granular view. It gives you within that 60-second, like how did your, the breakdown of that 60-second, how did your, let's say, search latency metric perform within that 60 seconds. It is not capturing the actual data points, but creating a histogram out of it to give you some idea of it, so that we can create all these P90, percentile statistics to understand more about it. We are using exponential histogram for that. It is not a fixed window histogram where, let's say, if we are talking about CPU utilization, we are not dividing it, let's say, 0 to 10, 10 to 30 or something like that, the fixed buckets. It is exponential based on the data. It decides our bucketing should be. Then the gauge in the gauge is where you want to schedule something to run on a periodic manner. Let's say I want to capture JVM usage every minute or so. That can be configured as a gauge. Let's say what use case I could think of is, let's say I just want to see what is the maximum JVM we have configured, so that we can get it from gauge, or some other Boolean type of metrics. Similar to traces, it is also comes, you will have to enable telemetry feature flag and metrics feature flag. There is an exporter setting where you need to define your exporter. By default, it comes with logging metric exporter, but it can be converted to, it can be configured to gRPC metric exporter, which write to your local running gRPC collector. So, the future work that we are doing is we are adding more and more instrumentations so that it's very easy for you to debug. We are also working on adding more controls so that you can control that also, like how you want to enable it. So OpenTelemetry specifically comes with a lot of configurations. So we are also working on a way how we can expose those configurations through the settings framework that we have. And specifically in the tracing framework, we are working on levels, something like which we have in logs, like you can enable, okay, I want to enable level 1 traces, level 2 traces. There are, because it creates a hierarchy, so there are challenges to it. It's also being discussed in the OpenTelemetry forum as well, but we are seeing how we specifically implement it for OpenSearch. Custom samplers, like I discussed, we are working on that. Performance analyzer, that dashboard which Gaurav has shown to you. So we are integrating, because there he discussed that, okay, we are going to have one reader which is going to read. So that is another collector. So what we are doing is we are combining it with the metrics framework only, so that you need to run only a single collector. So that's it we are doing. So we want all you to use that and contribute back, like what are your feedback on that. Thank you.